All right, let's get started. So today, or just some quick logistics off the bat. Again, the week 8 exercises are due today, and of course, if you need extra time, please let us know. Um, it is week 9 now, so you are so close to the finish line. Hang in there. I hope that in a week and a half, you can look back and take a deep breath and be proud of all that you've accomplished this quarter in this class and in other classes. But I hope you've been enjoying this class and learning a lot, and hopefully it has been feeling worth your time. And then the last assignment, project 2, that is due next Thursday, so on the very last day of class. Even if you don't have a chance to start right now, please make sure you go and accept the GitHub invite just because it expires after a week. Of course, if it expires, we could just send you a new one, but it'll just make your life a little simpler if you accept it. We posted in Slack, we made the last milestone optional. So that's also in the handout, but just in case anybody converted the handout to PDF before we changed it, we just decided that y'all have enough going on. And we still recommend doing it if you have the time. I think it'll be fun, and it will massively improve the performance of your project, but it's not required if you have a lot going on. Any questions about logistics? What's going on in this class? All right. So last class, we kind of talked about more high-level, system design-y sort of things, like how do you keep networked services up and available even when you're trying to scale to many, many users and your service is growing over time. Today, we are going to talk about how do you keep information safe and sound if you're providing some networked service. And really, this could be an entire class by itself. I don't even feel justified saying that this is a high-level overview, because that implies that we're kind of giving you a taste of everything or a view of everything, or we're not even going to have time to do that. This is really just a tiny slice of the topic. There are multiple classes you could take on this, but I just wanted to bring this up and start your brain thinking about this. And I think there are some interesting takeaways that we can learn from the many mistakes that I'll show you today as engineers in improving the things that we're designing. So just as a recap, if you're building a server, you are writing a program that is listening for connections from one or more clients. And I showed you last class this diagram of a connection being established between two computers. They each get a file descriptor on each end, and they can send each other bytes, and that goes to the other machine. The other machine can send the other machine bytes, and they just send each other bytes back and forth. But in order to have a productive conversation, you need to have some sort of expectation of, okay, this person is going to say this, then this person is going to understand what they said and going to respond. They need to speak the same language. If you just have, if I were to just pull up Jerry on Slack and just mash my keyboard and send him a mashed up string of text, he's going to get it and send me some question marks back because he has no idea what I was trying to say. And that's kind of the same deal in networking. These machines need to know how to talk to each other. So they speak some established protocol. The protocol is just a language that they both understand, so that, the client can send a message in a format that the server will understand. The server will receive that and will know what the client is talking about because they're both speaking the same language. Then the server can respond, however is defined inside of this protocol. And this is usually how computers talk to each other over a network, is there's some predefined protocol, they establish a connection, and then they speak the protocol. So, given all that you know about networked services and the sorts of things that you've seen in 107 and 110, various mistakes, maybe things that you've seen in your own internships or outside of class, what are some things that you might need to think about if you're trying to design a secure service that protects the information that it has? And maybe it might be helpful to flip this question. If you're trying to attack a service, what are some things that you might want to try doing? What are some ways we might expect servers to be vulnerable? We might be able to extract some information from them. Feel free to take a wild guess. I don't expect anybody to have actual experience with this. Yeah, so how would you take down the server? Yeah, exactly. So this is called a denial of service attack or a distributed denial of service attack, where you either send a lot of large messages or you send a ton of messages at the same time, or you send messages that take a long time to process, thus taking down the service because it's so busy responding to you that it can't respond to anyone else. That sort of attack, I mean, it is certainly an attack and it's certainly something to watch out for, but it doesn't usually expose any information because you're just crippling the service so that it can't do anything, including telling you things that you might want to know. Uh, sure, that's information from the server. It has it in its memory. Yeah, exactly. So you can actually misspeak this protocol. This protocol, you're supposed to speak a certain way. For example, in HTTP, you'll have like some content length header that says, I'm sending you 12 bytes, and then you're supposed to send 12 bytes. You're not supposed to actually send more than that. But what if you intentionally mess this up and you try to find ways that like cause the server to fail in strange ways and hopefully fail in a way that will send you some information? That's certainly something that you can do. Um, and I think if you ask a naive computer science student this question, like how would you attack this server? You start, your brain kind of goes to CS107 land, CS110 land, like, okay, what are, if there's some like memory corruption vulnerabilities or some buffer overflows or some remote code execution. Reality actually tends to be far simpler than that. So I will talk about that on the very, very last slide for half a slide. But pretty much all of today is going to be talking about defending against much, much, much easier attacks. And you may be disappointed at how simple a lot of this actually is. So I'm going to break this down into sort of 3 levels. The first level is don't give information to attackers that ask nicely. If an attacker asks you for like your password database or your like secret recipes or whatever sensitive information you're storing, and they like aren't authorized to get that information, then don't give it to them. Sounds obvious, but we'll talk about some cases where this has gone wrong. You also need to make sure that your dependencies, any like extra libraries or databases or extra pieces that you're using that you haven't built yourself, also don't give information to attackers that just walk up, knock on the door and say, hey, can I have all of your sensitive information? And then the final step is don't give information to attackers that don't ask nicely. When we start talking about like vulnerabilities and things where things are not supposed to happen that end up happening, but we'll talk about that at the very end. So first off, don't give information to attackers that ask nicely. Here's a really stupid attack. So we have an attacker that connects to a server and just asks, hey, give me your super secret sauce. Maybe the server is like a restaurant secret recipe database or something like that. And then the server just responds, okay, the secret sauce is MSG. And nobody would be this silly, right, to design a system that can have this happen. At least that's what we would hope. But if you look at this, I don't remember what year this was from. It was from a couple years ago. Panera Bread had a system up where you could just ask, get/foundation API users uramp something. This is saying get information about a user, and this number at the very end is a user ID. So you can just throw in any user ID, and the server will respond back with like all of the information that it has on this particular user, the email address, the like loyalty, phone numbers. I think they have addresses in here as well. Lots of stuff. And if you notice, this number here, which is the user ID, it actually happens to be sequential, which means that you don't even have to do any guesswork in guessing these numbers. You can just start at 1 and enumerate every ID and download their entire database. So this is bad enough it's bad enough that this happened in the first place, but Panera's response, unfortunately, is not uncommon, but it's just a case study in how not to handle a security breach. First of all, this security researcher contacted them and was like, hey, you have a serious vulnerability in your system. You need to fix this. And they blew him off and they said, we don't want to talk to you. They called him a scammer. They said, we don't want to do business with you. He wasn't asking for money or anything, but they said, we don't believe you. And then eventually the researcher just got tired of trying to get a hold of them. And so he went to the press. And within 2 hours, Panera put out a press release saying, oh, we did discover this issue. The issue is now fixed, and only 10,000 users were affected. Well, if you look at this number, this is what? 7,382,194. That's way bigger of a number than 10,000. Like, I don't believe that at all. And even worse, they didn't actually fix the problem, because this is just one API endpoint. So this is the API endpoint is just like the format of this URL. It's like /foundation API users uramp some number. That's an endpoint that gives you information about that particular user. But they had lots of other endpoints, and they also had other applications with the same exact design flaw, including like an enterprise catering app that had a bunch of like business and company information. Kind of silly. You can read the write-up here if you want to read more about. This is from the researcher that found this. This is silly and frustrating and disappointing. I'm also not trying to pick on Panera here. I think, as you see in the rest of this presentation, this is not a Panera-specific problem. This sort of attitude pops up everywhere, and is part of the motivation for teaching this class. So how do we avoid this? Before we can start talking about how to fix this, there are two principles in security that you need to be familiar with: authentication and authorization. They both start with A, they're both long words, they're both hard to type, but they mean slightly different things. So authentication means who are you? And this is established by supplying some credentials, like you give a username and password, you do some two-factor authentication, you like provide some biometrics or something, but it's establishing identity. And authorization is, are you allowed to do what you're trying to do? And this is established by some policy, that Ryan is able to access this information, Julio is able to access this other information. A user is able to access his own emails, but not the other emails of other people. And if you want to have a secure service, you need to have both. And I'm going to go through some case studies of where people have had one or not the other. It's not good enough to have authentication without authorization. It doesn't even make sense to have authorization without authentication, because then you don't even know who you're talking about. But the way that this commonly gets used, so I'll just draw here a very common setup for like how clients will talk to servers. First, the clients will log in. You go to a website, you click the login button, you type your username and password, and your browser sends to the server, hey, my username is cactus and the password is prickly. And the server will go in the database and verify that this user actually exists and that the password is correct. And then the server will say, okay, that's fine. Next time you want to talk to me, use this token. Now, this token might seem a little bit strange. We could just give the username and password on every subsequent request. Like every time this client wants to do anything, just provide the username and password. And that would work fine. The problem is that the browser would need to remember the username and password. And we try to minimize like how much that information is exposed. So ideally, you log in, you type your username and password, the browser sends it one time, server responds with a token that the client can use instead for subsequent requests, and then we just forget the username and password. Don't store it in memory. So then whenever the client wants to do anything, say you've logged into the email website and you're trying to download your emails, the client can say, show me emails for the user Cactus. My token is ABC123. The server will have to first validate that that's a valid, legit token and that it belongs to Cactus. And then it will need to make sure that Cactus has the permission to view emails for the user Cactus. And if that is reasonable and that seems right, then the server will respond and say, hey, here are the emails for the user Cactus. So just to highlight here the authentication and authorization. Authentication, again, is where clients need to demonstrate their identities. So you have to provide something that only you would know, like your username and password or your secret token that the server gave you. But you have to present something to demonstrate your identity. And then for authorization, the server needs to verify that you actually have permission to do the thing you're asking to do before it carries out that request, right? If this check was missing, this would be terribly insecure, because you could log in as somebody and then ask for the emails for somebody else. And if the server didn't verify the permission check, then they would just give you the emails, and that's not good. I mentioned the tokens aren't strictly necessary, but they are useful. If you've ever heard of cookies in the context of like web programming, a cookie is just a token. All right, so let's talk about some horror stories. So the first one that I want to mention is life without authentication. So there was no authentication. First of all, Panera is an example of no authentication at all. This application that I'm going to talk about had some authentication in most places, but there was one place that they missed that didn't have authentication, and it caused huge problems. So what is SaltStack? Last week we were talking about like cluster management and how a lot of times you have clusters of a lot of machines, maybe hundreds or even thousands of machines, and you can't manage that many machines by like SSHing into them each individually. That is going to take way too long. You're going to make mistakes. And so instead, people have automation solutions. SaltStack is one like automation system where you set up these nodes. These nodes will like, they're running your application, and they're also running this like minion program that will connect to this master server and say, hey, my CPU usage is 68%, or like whatever. They'll check in with statistics. And if you have some system administrator that is trying to control these nodes, it can say, hey, please update all the servers to version 10. And then this SaltStack master can send a message to all of them saying, hey, install version 10. And then the minion will go and do that upgrade. Does this make sense? And this is fine. All of these requests, all of these communications, they are all authenticated and properly, and they have proper authorization checks. So this system is fine. The problem is that an attacker could connect and could call this one API endpoint. They could invoke this one function that was not supposed to be exposed to the network, but they accidentally exposed it to the network, called sendPub, which will enqueue something into the job queue. So they could say, send pub, install Bitcoin miner, and kill SSH. And there is no authentication required for this. And because there's no authentication, anybody can connect and say like, hey, add this to the job queue. And then the master is in the queue, so it sends it out to all the nodes. And it says, hey, install Bitcoin miner. And well, what happened? Actually, so this was 3 weeks ago last year. I forgot to update the slide. But 3 weeks ago last year, companies' entire clusters started becoming unreachable. Like they couldn't SSH in, they couldn't load anything on the web page or anything. And many of them were targeted with this like Bitcoin mining program plus a backdoor to like log in and check in on things. And this hit so many different companies. I think there were like 20 in the span of 2 days of like high profile companies that were hit by this. And it's a nightmare to fix. First of all, you can't even SSH in, right? Like they disabled SSH. So how are you going to get in? And then once you get back in, how do you verify that the attackers aren't still hiding, right? Like if they got root access, then they could just put up a facade that looks like they're gone, but actually they're still in the system. Like you kind of have to wipe everything, and it's a huge mess. Here are some more technical write-ups if you're interested in how this worked. So this is what happens if you have authentication in most places and you forget it in one place. What about authorization? So again, authentication is like you need to ensure you know who you're talking to. What if you do know who you're talking to, but you forget to verify that they have permission to do the thing that they want to do? And for this, I'll talk about a company called LocationSmart. So LocationSmart is, or possibly was, I don't know if they're still around. They were a location tracking service that would sell location data of cell phones to like law enforcement, companies wanting to track corporate devices, that sort of thing. And so they would partner with every major cell phone carrier. And so they knew like the location of basically every cell phone. And then they would sell this data. This, first of all, was probably illegal to begin with. I don't know all the specifics here. This data, the location data was supposed to be used for like 911 calls. That's the intent. It was not intended to be sold to companies wanting to track corporate devices. But anyways, this happened. It was also impossible to opt out. Like it's not like your phone was sending the location to this company or even to your provider. The provider was triangulating the location using cell phone towers, even if you didn't provide it, and then being provided to LocationSmart. So this affected like everyone. And this company had a demo website where you could put in your information, your like first name, last name, email address for marketing, and then you put in your phone number, and it would send your phone a text message. You'd have to opt in, but once you confirm from the text message, then it would show your location on a map. I don't know why they had this as like a demo, maybe just to like prove that they were legit and they actually did know where your phone was, but I don't know. This seems like a bad idea from the start. But anyways, the way that this worked, there are several requests involved here. First, we have a subscription request. So when you go to that box and you type in your name and your phone number and you say, hey, like send me a text, I do want to opt into this demo. Then your browser sends a request to LocationSmart saying like, hey, here's the data, like here's the phone number that I'm trying to track. Then the server will respond. And it responds with a bunch of information. There's two things here. So first is the token, which is this like, it's the authentication token that you use for subsequent requests. So this is how the server will know going forwards who you are. The client is supposed to remember this token and then submit it in the future requests. And then it says privacy consent required true, meaning you need to accept the link in the text message. You need to opt in via SMS before we will give you this information. Okay, so this is fine. I just shortened this request so that it'll all fit on the slide. And that's the subscription request. So we're trying to opt in. Then the browser will repeatedly send a status check message saying like, hey, has the phone opted in yet? And the server will say, no, subscription not active. Like you were asking about this phone number, but that phone number hasn't confirmed that they want to like opt in yet. And the browser will do this over and over repeatedly, kind of just like busy waiting, checking until you accept the thing on your phone. And once you do opt in, then it will send the same request again, and the server will respond saying success, saying, hey, the opt-in finished, like we're done here. So once the status check is done, finally we send a location request saying, hey, get me the address of this phone number, and the server will respond with the location data in XML format. Everyone understand how this works? This is like how it is supposed to work. This is the design. There's 3 steps. You first ask to opt in. You do a request saying like, hey, I want to see my location data shown on this map. And then like you just keep repeatedly asking, is it ready? Is it ready? Is it ready? And then once you have confirmed on your phone, then this will succeed. It will return okay. And then you send a location request saying like, okay, what is the actual location data? And that is what shows up on the map. So this is how things worked. Like back when this demo was live, you could actually just like open up the network tab in your like browser tools to see what requests and responses are being made, and just like do the thing, and you would see this. Like this is how it worked. You should wonder, what if we just like remove this step? What if we got rid of this middle step? So what if we just made a request and didn't confirm it on the phone and just immediately asked for the location? This is how the JavaScript client was programmed, but we can change that. Like what if we just omit this middle step? So if we skip this and immediately send a location request without consenting on the phone, then the server does do the right thing, and it returns us an error saying like, hey, you haven't consented on the phone yet. So that's fine. But if we change one little thing here, so this request type says request type equals LOCREQ. I think location request is probably what that is short for. If we change that and tack on a .json, if we say location request .json, so before it was responding us, it was sending us a response in XML format. If you've never heard of XML or JSON, it really doesn't matter. They're just 2 ways of like representing information. I don't really know why they had both, but before it was using XML by default. If you tack on a .json, then it will respond to you with the information in JSON format. But if you tack on a .json and you omit this middle step, then it will send you the location info regardless of whether the user consented. And this is horrible. Like this has location data accurate to within like 10 meters for anybody with a cell phone. Right? If you think about the potential for all sorts of crime, this is really bad. I don't know. You can imagine lots of scenarios where this would not end well. And it is so easy to exploit. You just, put in a subscription request for somebody else, not even you, and then immediately ask for the location in JSON format, and you get it. It's that simple. So .json. I think that this was probably a bad case of copy paste. So, by the way, here's some context for what happened, and then here is the link from the researcher who found this on what happened. If you want my take on what happened here, my guess is that they probably wrote the JSON version first, the one that returns to you no matter what, and then they probably copied and pasted it and changed it to return XML, and then they probably realized, oh hey, by the way, we should probably do an authorization check to make sure that the user has actually consented first. That might be a reasonable thing to do, and then they probably forgot to go back and change it on the JSON endpoint. Any questions about this? So this is obviously bad. All the things that I just showed you, they're trivial to exploit, extremely easy to pull off, very, very simple, and very bad. Okay, serious consequences. How do we prevent this? So if you are writing a web server, you really definitely should not be reading bytes from a file descriptor and doing all of this stuff with a file descriptor. It's too low level. There's too much to think about. You're going to mess up. The standard approach is to use some sort of web framework that will handle all of that communication for you. So in whatever language you're working in, you just write a function that handles a request for a particular endpoint. Remember, an endpoint is Panera had that endpoint that was /whatever/user ID. That's an endpoint. If somebody makes a request to that endpoint, then the library or the framework will receive that request. It will gather all the information from the client and will just call your function saying, hey, you got a request for this particular endpoint, and you just write a function that is for that specific thing. And what you could do is you can configure this framework to say hey, if anybody's asking for this thing, make sure that they have proper authentication and authorization. You sort of build it into the framework so that by the time it reaches your application code, it has already done all of the authentication and authorization checks. You can't forget to include it in your code because it's not in every single one of your functions. It's not something that you copy and paste at the beginning of all of your functions. It's something that is done centrally inside of this library that just handles it happens on every request, and you don't need to worry about it. You can still make mistakes though. It might be the case that on certain endpoints you need to have they have to be authenticated, and on other endpoints they're not. For example, say you're running an email website. You need to be authenticated and authorized in order to read your emails, but loading the homepage, anybody can load the homepage. You don't have to be logged in. And so it is still possible to mess up the configuration of this. But because all that configuration is in one place, and it's very short and simple, and it's easier to audit, it's easier to double check. But if you want to take things one step further, you can use a stronger type system to make it impossible to get information without having the proper privileges. So there's a Rust web framework called Rocket, which was developed by Sergio Benitez. He's a PhD student at Stanford. And this has an idea called request guards, which are types that require validation to be done in order to create any values of that type. So for example, let's say that you're working on a hospital website that has medical records. So you're going to write some code that talks to the clients and handles the requests and sends the responses. You're also going to have some code that loads information from the database. If you create a request guard, if you create a type called a super user, and you implement your database loading function like this, you say health records, and you have to be passed a super user in order to get the records. If this is the part of your application that is loading data from the database, and you have to have a super user value in order to get there, and if that super user can only be created from a request that has the proper permissions, then it is literally impossible to have an authentication or authorization bug here, because the only way that you can get data from the database is by calling this function. the only way to call this function is to have a user that is a super user. And the only way to have a user that is a super user is to have received a request that has like proper authentication and authorization. And Rocket is what is creating the value here. So I'll talk about this more next week on the very last class. It's a really powerful concept. And it could have avoided all of these bugs. Like if SaltStack required a sysadmin value in order to add something to the job queue, that vulnerability could not have happened. All right, so this is level 1. Like make sure that your application itself does not just give out information to anybody who asks. That seems like a bad thing to do. Level 2 is to make sure that not only does your code not hand out information, but you also have to make sure that the components that you're using don't hand out information. We've been focusing on this, your code running on these compute nodes, but your compute nodes also use like a database, and your database servers also have IP addresses, which means that it might be possible for somebody on the internet somewhere else outside to send a request directly to the database and ask for information. And if that happens, you need to make sure that these databases don't just give everything out. I mean, ideally, you don't want that to be possible at all. You want to put these like behind a firewall or something so that nobody else can talk to them. But anyways, so there's a database called Elasticsearch, which is a very popular database for doing all sorts of like flexible data analysis. It's really useful because you can just throw up an Elasticsearch cluster, run a couple of machines and just throw data in there as it comes in. It's sort of like an unstructured search. And so you don't have to like do a bunch of data processing to, find the specific fields in the data that you're looking for. You can just put whatever data you want in there and then quickly run queries on that data. And it works really well. It's a very popular database that's used in a lot of different places. The default settings for this database are to only respond to local connections, meaning connections from the machine that Elasticsearch is installed on. It's still using networking, but it's only responding to network connections originating from the same machine, which means this is not really useful. Like if you're going to use this inside of a cluster of machines like the diagram that I was showing before, well, in that context, we had our compute nodes that were on a different machine that were sending requests to the database machine. Those are separate. And so this wouldn't work because by default, Elasticsearch would not respond to those connections. And so you say, hey, no problem. I'll just change the configuration to accept external connections. Everything is fine. And lots of people do this, right? This is the natural train of thought. And if you search on Google, Elasticsearch data breach, this search was from last year. It would be fun to search it again if you want to do that right now. I'm sure there's plenty more from the last year, but this was from last year, and just like I was expecting to find several hits for the same breach, but almost every one of these is a different data breach. We've got one 250 million Microsoft customer support records, 24 million credit and mortgage records. Millions of people and businesses at risk. All like so many data breaches, and these are entirely preventable. I also there's a service that you can sign up for called Have I Been Pwned, and they do like monitoring of data dumps. So they will send you an email if they find your information in data dump. It's a free service. You can sign up. I don't know if it's all that useful. There's not really that much you can do. You're just like, okay, I'm screwed. But I'm signed up, and so last year I got an email saying, hey, your data was compromised in a company's data breach involving 103 million records. But the twist is nobody has any idea which company. Somebody just found an Elasticsearch instance on the internet. Nobody knows who it belongs to. People tried to make guesses based on the sort of information that was inside. Like people were guessing this is probably some like CRM, some like, I don't know, customer service database or something like that. You can sort of read about the drama. But this sort of stuff happens all the time. And what is the response? Well, Elasticsearch says it's not our fault. According to Elasticsearch, these breaches are caused by a poor understanding of Elasticsearch security and how the software works. Reports usually involve instances where individuals or organizations have actively configured their installations to allow unauthorized and that should probably say unauthenticated. This is just copy and paste. Unauthorized and unauthenticated users to access their data over the internet. Okay, well, that is true, right? All of these breaches that I just mentioned, they're just sitting there, like their database is just sitting on the internet. And I'm just like highlighting Elasticsearch here, but if you Google S3 data breach or MongoDB data breach, you'll find just as many cases. So this is not an Elasticsearch specific problem, but I do think it's worth like asking a little bit more about, well, why is this happening and what can we do to prevent this? There are 3 reasons that I'll give you. So the first reason is bad default settings, right? So databases commonly have a default username and password. And many of these databases were insecure by default. So MongoDB used to accept all network connections by default. Elasticsearch is slightly better, right? It will only accept connections from the host that it's running on. But you know, this was a huge problem. I think we are slowly getting better at this, right? Elasticsearch's defaults are not quite so bad, but there's still a lot of room for improvement. Another problem is negligent and inexperienced engineers and system administrators. Like Elasticsearch is right. These breaches are caused by people who are just like actively configuring their instances to be accessible everywhere on the internet from anyone, right? They think I need to access my database from a different server, so let's just open it up on the network, not realizing that, okay, well, you just opened it up to the entire internet. And this is a systemic problem, right? This is not specific to Panera. This is not specific to any of the companies that had data breaches that I just listed there. This is happening at like Microsoft too. Security is a poorly understood afterthought in a lot of organizations. The priority is just shipping features and getting stuff out the door. Security comes later. And I think we have some improvement in this area. There's like more legislation that is coming out. I think there's also more like, I don't know. There is PR backlash every time a breach happens, but I don't know if it actually matters that much, right? People forget pretty quickly, and people move on. Like Equifax had a horrible. I'll talk about Equifax in a little bit. Equifax was a huge company that leaked data for every adult that has a credit history, and people were very upset, and their stock price crashed. And then like a few months later, it was back to normal. So, I don't know if we're improving that much. There's certainly a lot of room for like, I don't know. We can have a conversation about this if you're curious. The third reason, and I think which is the most interesting one to us as engineers, is we have been designing systems where the path of least resistance is bad security, right? It needs to be harder to do things wrong than it is to do things right. If you look at Elasticsearch, it's not useful to have a default setting that is to accept only local connections, right? Sure, that is like, secure by default, but everybody's going to change that. And it's easier to just, open up the instance to all connections than it is to configure it so that it is only accessible to your compute nodes. You have some authentication and authorization going on so that like only those compute nodes, they have to prove their identity and they have to like be the only ones authorized to access data. And I think in many places we're only starting to think about this. And this is something for you to think about in the systems that you work on. We really need to think about how to design things that are secure by default. If you joined the systems track because you didn't want to think about people and how people are using software, you joined the wrong track. Or I guess there are a lot of people in systems who have that attitude. When something goes wrong with like people using interfaces, there was this. This is random, but I just came to mind. There was this thing in Hawaii where somebody like accidentally triggered, I forget which alert it was, but it was like an island-wide alert, like an incoming missile alert, or maybe it was I think it was incoming missile alert. And it like went on all the highway billboards. It was sent to all the phones. It caused like mass panic. And it turned out that it was just some operator that clicked the wrong button. But it was totally not the operator's fault. Like if you look at the UI of the web page that they were using for that, it was like such a mess and so hard to use. Is you can't always just like immediately point the finger at the people. You have to design good interfaces that are hard to misuse. And I think in systems we have an attitude of, okay, it's a programmer's fault. Like whoever was using my software, it's their fault. They used it incorrectly. And like, yeah, that's it might be true, but also we need to be thinking about how do we design software that is not as hard to misuse. Like I think Rust is a really good example of this. It is a language that is designed to be hard to mess up. C++ is the exact opposite. It boggles my mind how every time they add a good thing to C++, like the default is undefined behavior, and like if you don't use it exactly correctly, then you're in trouble. There's also a lot of work to be done in like building systems to improve security for things we don't have direct control of. Like if you're part of designing a database system, okay, you need to design this to be like easier to use right than to use wrong. If you're working at a company that is using a database, you need to make sure that you at the company are using the database correctly. But what if you're not working on the database and you're not working at that company? There are a lot of people that are trying to still, play an active role in improving this across the industry. For example, GitHub just hosts code. That's what they do. They're just like a Git host. They just store your code. But somebody at GitHub said, we have much more opportunity than just storing people's code. People store code on our platform. They make lots of really obvious mistakes in code. Like they commit passwords and API keys into open source code. So like you could just go on GitHub and do a search for a variable name that stores an API key for some provider, and you'll find tons and tons of these things. It's a big problem. And GitHub said, we can do better than this. We can actively scan code for this. And today, like if you try committing an API key from like a well-known example into a repository, they will probably reject your commit and say like, hey, you probably shouldn't do that. There are also like other systems being developed to proactively scan for open databases or things like this. And there's a lot more work to be done. So that's level 2. Make sure that your dependencies, the things that you're using, aren't just going to hand out information willy-nilly. Well, what about level 3? So we want to make sure that we also don't give information to attackers that don't ask nicely. And let's say that you're imagining you're trying to hack into a system. How would you go about it? We kind of talked about this at the beginning. You want to try the easy things first, like finding obvious weaknesses. Social engineering is something we also didn't talk about, which is a really easy way to break into systems. What if that doesn't work? Again, if you're a naive CS student coming from 107, 110, you're like, all right, now it's time for buffer overflows. Now we're going to start like hacking things. And like, yes, this is the time to start hacking things, but not by looking for buffer overflows of your own. You don't even have to do that. The next best, very, very, very easy thing is to use known vulnerabilities. Most of the time, you don't even have to find vulnerabilities yourself because people are so bad at updating software that you can just like look for security bulletins and say, oh, hey, this very popular software has a vulnerability. I bet this person over here hasn't patched and like updated their system yet. I could probably still use the same exploit on this person's system. So 2 quick examples. There was a ransomware called WannaCry, which would encrypt all the files on your computer and demand Bitcoin payments before you can get those back. The impact was huge of this virus. It estimated it infected 200,000 machines and caused up to $4 billion in economic damage. It infected the NHS in the UK. So it infected like computers, MRI scanners, blood storage refrigerators. Like this is a bad situation. And let's look at how this happened, because WannaCry was entirely preventable. So at some point, the NSA discovered a buffer overflow in the Windows Samba stack. They did not share it. They used it for espionage or offensive exploits, but Microsoft ended up discovering it independently and fixing it in March of 2017. A month later, so in April, there's this hacking group called the Shadow Brokers. They announced that they broke into the NSA, stole the exploit from the NSA, and published it online. So Microsoft fixed this, and they issued a security advisory saying, hey, you need to update. They didn't actually release the exploit itself. That would be irresponsible. But the shadow brokers went and they released the exploit. So they just posted it online, and people started downloading it and making their own exploits. And in a bad situation, this would have happened like 2 days after they posted it. But WannaCry didn't start spreading until May. Okay, so people had quite a lot of time between March and May to update their systems. Guess what? They did not. And if people had just applied these updates from March, WannaCry would have been completely prevented. There's another case in Equifax. So Equifax was the company that I mentioned earlier. Equifax is a credit score provider. I don't know what the official term is. But they have like your credit history and lots of sensitive information on every adult with a credit history in the US. So 143 million people. How did this happen? Well, in March of 2017, Apache released a security advisory saying, hey, there is a security vulnerability in Apache struts. So I mentioned web application frameworks before, which will like take the incoming requests, do some processing, call your like application code functions, and sort of facilitate all of that communication. Apache struts is one of these frameworks, and there was a vulnerability in it. So it happens. But guess who didn't update? And so in mid-May, so they didn't update for 2 months. In May, attackers use this vulnerability to get remote code execution. Then they start, working their way through the Equifax system, breaking into other computers. In July, Equifax finally figures out that this is going on, but they don't say anything, and they don't announce until September that they've been hacked. It's a total mess. Again, another example of like what not to do in handling a security incident. There's some more links here that you can read on. But again, entirely preventable if people had just updated. So as engineers, what are some things that we could take away from this? First of all, like you yourself should be updating. Updating might be annoying, but being compromised is so much worse. This applies for the software on your machine. It also applies for like libraries that you're using and frameworks. I think GitHub is having huge impact on this because like if you're using a library, say you're developing a JavaScript app and you're using a library that has a known vulnerability, GitHub will actually open an issue for you like on your repository. They will create a pull request. All you have to do is press like accept in order to update. But most developers, you create the project, you start using a library, you pin it at a certain version, and then you just never update. And it's important to update. A lot of the last decade has been spent trying to figure out how to get people to update their systems. It's really important. It's also important as an engineer to, if you have like ideas on how to improve this is a huge problem. It sounds like a very simple problem, but it's actually a very complicated problem that is very important. And so somewhere to work. It's also very important to like minimize your attack surface. So if you have any component of your project that doesn't need to be exposed to the internet, then don't expose it to the internet. It's a simple strategy, but it's really important. So the very, very last thing, like if you're an attacker and you've like, scanned and like looked for low-hanging fruit, you've tried social engineering, you've tried known vulnerabilities, then you can start thinking about zero-day vulnerabilities. The last resort for an attacker is to find a brand new flaw. This is very hard. I shouldn't say it's very hard. Depending on the code quality, it can be hard. In some projects, it's unfortunately easy. But in well-secured projects like Chrome or like iOS or the kernel, it's hard. You have to pay people to do this. So if you work at a larger tech company, they will have a dedicated team that tries to hack your system. It's actually really important that you have a dedicated team and you're not just having the engineers who wrote the code try to attack the code, because if you wrote the code, you're thinking about how the code is supposed to be used. If you're trying to break into a system, you need to be thinking about how the code is not supposed to be used. You're thinking, okay, this code was intended to do this thing. How can I fiddle with things and make it do something completely different? Some companies also have bug bounty programs. This is a really good idea. And if you need high security, you should not only be looking for bugs in your code, but also in the dependencies that you used. In 2014, a lot of people realized like almost literally everyone is using OpenSSL. OpenSSL is a library that implements TLS. So whenever you go to an HTTPS website, you're using OpenSSL. Whenever you SSH into anything, you're using OpenSSL. But nobody pays for it. And it like people realized that OpenSSL was being maintained by this like one guy that was unemployed and like had a bunch of health problems. And they're like, this is critical software and nobody is paying for it. If you've ever heard of Project Zero was created because of Heartbleed, and their mission is to look for bugs in dependencies. So that's all I have for today. I will see you on Thursday. Thanks for coming and have a good rest of your week 8.